Hi, I am Anubhav and I'll be presenting our work titled Measuring Style, Similarity in Diffusion Models, which is due to be presented at ECCV 2024. Why are we interested in studying style with respect to diffusion models? Now, generative models like Stable Diffusion, Dolly, etc. are being widely used by the community. And while being extremely useful, prior works have shown that these models remember and often replicate content from their training data. But then why is it crucial to understand if and how they replicate data? Well, if we understand this particular nuance, we can help artists know if and how their work is being used. We can also help users understand if they would run into potential copyright issues. And this understanding provides insights into the inner workings of these systems. But before we can begin to understand this, we need to define what style is, and there is no easy way to do this. Style is basically a subjective property capturing complex interactions between colors, textures, etc. But it is primarily a global property of an image instead of focusing on some particular semantic details in the image. Now, there are named artistic styles which are often associated with certain artists, and we leverage this and define style as collection of image characteristics that can be identified with an artist or artistic movement. There has been prior work concerning style, but most of the work has focused on either transferring style or it has ended up focusing more on the semantic similarity in the images. Most of these works have used some form of self-supervised learning, but we feel that since style is inherently subjective, a good style structure should be aligned with human perceptions and definitions of style. For this reason, we create a style attribution dataset, Lion Styles, in which images are associated with the artist that created them. A few details on this dataset. It's based off of Lion Aesthetics, and we ended up using Clip Interrogator and finally released a dataset which has 512,000 images and 3,840 style tags. Now, how do we solve the problem of extracting style from an image? We basically want a model that should be invariant to semantic content and capable of disentangling multiple styles. For our feature descriptors, we use some form of embedding from vision transformers, and in order to train these embeddings, we use a combination of multi-label contrastive loss along with standard self-supervised loss. While training, we diverge from standard self-supervised training as we reject the photometric augmentations like Gaussian blur, color jitter, since they can alter the style. Instead, we only keep augmentations like flips, resize, and rotation. Now let's evaluate the performance of our method. We perform zero-shot evaluation across multiple datasets on a simple style retrieval task. We split each dataset into a query and database part, and given a query image at test time, we evaluate whether we can find the ground truth style in its nearest neighbors from the dataset. As seen from this table, our method outperforms all the methods on this style retrieval task. But why do we perform better? We found out that our multi-label style contrastive loss was key in achieving this performance, and also the fact that we carefully curate non-photometric augmentations during our training. Going deeper into the performance analysis, even though our method outperforms all baselines, our performance on WikiArt was 64.5%, and we tried to understand what could be happening. What we found out that our model was getting consistently confused between impressionist painters. That's primarily because all of them painted just the landscapes, and also a fact that most of the density of the heat map is concentrated on the diagonal, which suggests that model can correctly predict the movement, but is probably getting confused between the artists. This analysis suggests the nuanced nature of this task and also suggests that the upper limit for accuracy in this task might be considerably lower than 100%, even for a typical human evaluator. We ended up doing a human study, and that's basically what we found out. Now that we have established that our method can reasonably disentangle style, can we do style matching on stable diffusion generated images? For this, we needed a query dataset, and we ended up creating one synthetic styles dataset using three kinds of prompts: user-generated prompts, simple prompts, and content-constrained prompts. For each of these prompts, we generated 4,000 images. Now let's discuss some analysis on this dataset. So starting with, we created a list of 96 artists, primarily sourced from WikiArt and supplemented by a few contemporary artists. For each of the artists, we compute a prototype vector, which is basically an average of the embeddings of all the images of that artist in our dataset with respect to our CSG large model. Then we generate an image of an artist using a simple prompt, like a painting in the style of this artist. Then we compute a dot product similarity between this embedding and the prototype vector, and we call it as GSS score. Similarly, we compute CSS score where the prompt is constrained in the sense that it is like a woman doing something in the style of this artist. What we found out that ST 2.1 is much more capable of emulating some artists than others. We also see that GSS and CSS scores are highly correlated, indicating that our feature vectors represent style much more than semantic content. After careful inspection, we hypothesized that a single image style similarity score of less than 0.5 indicates the absence of any style copying, while a score greater than 0.8 can indicate the presence of style. Now we saw a few artists diverging away from the identity line in the previous chart. How far the score is diverging away from the identity line could reflect how far out of distribution the subject in the prompt is for the artist. This could serve as an indicator of the generalization capability of the artist style. For this analysis, we selected dog as the out of distribution subject and we found out that ST 2.1 generalizes well to the style of artists who have diverse paintings. Basically, the artists with a lower intra-cluster similarity who fall on the bottom left corner of this chart, and this is evidenced by their almost similar GSS and CSS scores. Next, we did a quantitative analysis of our method on the Lion styles dataset, and our method outperforms all the prior works on simple prompts. Additionally, our method consistently outperforms both baselines in content constraint scenarios. This indicates the robustness and effectiveness of our approach in dealing with a variety of prompt complexities and content specifications. In conclusion, we release a new dataset, Lion styles, that associates images with their styles. We propose a new method, contrastive style descriptors, to extract style from images. And we show indicators on how likely an artist's style is to be replicated in stable diffusion through a style attribution case study. Thank you.